In this video, we're going to look at the conditions that must be satisfied in order for the binomial probability formula to be used. The way that we set this up was always about counting the number of successes out of a fixed number of trials. So that's actually the first condition, is that in order for binomial to be appropriate, there must be a fixed number of trials. So an example of a situation where that wouldn't work is if I said, how many taxis do you need to wait for until one stops for you? Well, it's a perfectly good probability question because I could say, what's the probability that you need to wait for more than 4 taxis? But it's not a fixed number of trials because in principle, you could wait for hundreds or thousands or millions of taxis. So that condition needs to be met. There needs to be a fixed number of trials. Like I'm going to take 10 shots at the basketball hoop and then I count how many I succeed in. The next condition is that there can only be 2 possible outcomes. So in all of our situations, it's either I got the basketball in or I didn't, or a player won the game of badminton or they didn't. So that's important, and that's actually the clue is in the name, binomial, bi meaning 2. So there must be 2 possible outcomes. There is a fixed probability of success, so the probability can't change on each day. So on each trial. So for example, if we looked at the probability of it raining on each day, and let's say on the 1st of the month throughout the year, that's no good because it's more likely to rain at certain times of the year than others. It's not the same probability each time. It's not 20% chance of rain each day. It varies throughout the year. So that would be no good. The final probability is that the events need to be independent of each other. So succeeding in one shouldn't make it more likely to succeed or more less likely to succeed in the next. Now, that's a tricky one to determine, but there are plenty of situations where you could be skeptical about whether repeated trials or whether your trials are really independent of each other. Even with the basketball case, it might be that as I take my basketball shots, I'm kind of practicing, so I might get better. It might be my first shot, I'm kind of nowhere near. So I think, okay, I need to throw it a little bit harder, a little bit higher, and I get better. In that case, it's not independent because the initial attempts, if I get them in, I might think, okay, I'll just do the same thing again this time. So getting a shot in actually might improve my chances of getting the next one in. Let's have a look at a number of examples and think in each case, could we use binomial probability? So I encourage you to pause each time and look at the question and think, could you use binomial there? So first one, the number of games a football team wins in its next 10 matches. Could we use binomial there? Well, I think no, and I think this one, we fail to meet condition 3. So the fixed probability of success, but presumably if your football team is playing 10 different matches, it's playing different opponents. If you're playing an easy opponent, then the probability might be quite high that you'd win. Whereas if you're playing a really strong team, it might be low that you'd win. So it fails 3. So that one's going to get a cross. It does meet some of the others. So I do think it's certainly got a fixed number of trials, 10 matches. There are only 2 possible outcomes. Even though there are draws in games, we're just thinking how many wins. You either win or you don't. Independence, maybe not, because maybe if you win 3 in a row, you're full of confidence and suddenly you're likely to win your next. Next, the number of 6s rolled when rolling a biased dice 20 times. What do you think? So actually I think this one's fine because the bias doesn't matter, okay? There are a fixed number of trials, 20. There are only 2 outcomes in the sense you either roll a 6 or you don't. There is a fixed probability of success. Even if it's biased, it's still going to be the same probability each time. And the trials are independent because dice rolls don't. If I get a 6 on this roll, it doesn't make me more likely to get one on the next. Next, the number of rainy days in the next 7 days. What do you think? So I think no for that one. And there are a few. So maybe it's independence there because if it's been raining non-stop for the first 4 days, do you think that affects the probability on day 5? Probably, I would assume that we're just in a rainy part of the year, or we're in the middle of a storm or something like that. So I think they're not independent there. If it's been completely dry for 4 days, you'd probably think it'll be dry again the next day. Also, the probability might not be the same. So I think that one's not quite so good, but maybe a little bit more difficult to see in that case. Okay, the number of students who are late to school out of a group of 30. Well, certainly a fixed number of trials because it's 30 of them. Only 2 possible outcomes because you're either late or you're not. Fixed probability of success, not sure. Independent, I doubt it. For example, if there's a big snowstorm, then probably many of them will be late. Or if they catch the same bus and that's late, then maybe lots of them will be late. So I think that one definitely fails independence. Finally, the number of goals scored by a team in the next 12 games. What do you think? Can we use binomial there? So definitely not. There are a fixed number of trials, 12, but there aren't 2 possible outcomes because it's not win or lose or score or don't score. It's the number of goals, and you could score 0 or 1 or 2 or 3 or 4 or anything. So there's not only 2 possible outcomes. Even if the probability of success is the same and the trials are independent, there's no way to use binomial here because there aren't only 2 possible outcomes. So it's definitely not binomial. All right, hopefully that was a useful review of what the conditions are, and you feel confident deciding whether or not a situation is a good candidate for binomial probability. This is often the last part of a question to say, comment on the suitability of a binomial distribution in this case. So you need to be able to think critically about whether you could use them in the different sorts of questions.